In this chapter, we study the vehicle routing problem with split deliveries. The defining feature is that one customer's order can be delivered by more than one vehicle. Allowing splits can reduce wasted capacity and extra mileage, but it also increases decision complexity because the routing and the delivered quantities must be coordinated. Split deliveries matter because capacity constraints often create inefficiency in standard vehicle routing. A vehicle can be forced to close a route early simply because the next customer's full demand does not fit. With split deliveries, the vehicle can use its remaining space to partially serve that customer, and another vehicle can complete the remainder later. This tends to improve utilization and reduce unnecessary trips. Our scenario is last-mile urban distribution for a large e-commerce operator. Every morning, many orders must be delivered from a distribution center outside a dense city. Because the fleet includes vans with different capacities, splits are especially useful. A large order can be started by one van and finished by another van that still has spare capacity and is traveling in the same direction. The operational benefits follow directly from better packing and better routing. You avoid dispatching half-empty vehicles, and you reduce detours caused by rigid one-visit requirements. In dense cities, those savings translate to fewer vehicles on the road, lower total mileage, and lower fuel consumption while maintaining service quality. This deck uses 9 tiers. We start with a mixed integer linear formulation that explicitly models both routing and delivered quantities. Then we move through a sweep heuristic and ant colony optimization, followed by reinforcement learning with graph neural networks. Finally, we expand to digital twins, multi-agent coordination, human and artificial intelligence collaboration, ethics, and a quantum-inspired view. Tier 1 builds a rigorous baseline as a mixed integer linear program. The model chooses which arcs each vehicle travels and how much each vehicle delivers to each customer. The goal is to minimize total travel cost while ensuring every customer's full demand is satisfied and ensuring each vehicle's capacity and route feasibility constraints are respected. This slide defines the node set, including the depot and the customer nodes, and it introduces the set of vehicles. These sets define the indexing structure for the routing and delivery decisions. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. This slide defines the main parameters: customer demands, vehicle capacities, and travel costs between nodes. These are the fixed inputs the optimization must respect. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. This slide defines the decision variables. The routing variable indicates whether a vehicle traverses an arc, and the quantity variable indicates how much a vehicle delivers to a customer. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. The objective minimizes total travel cost across all vehicles and arcs. Minimizing travel cost is a common proxy for distance, time, and fuel consumption in routing problems. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. Demand satisfaction forces the total delivered quantity to each customer to equal that customer's demand. This is the key modeling change that makes split deliveries possible. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. The capacity constraint ensures that each vehicle's total delivered quantity does not exceed its capacity. This keeps routes physically feasible. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. Flow conservation ensures route continuity. If a vehicle enters a node, it must also leave it. This prevents disconnected route fragments. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. The depot constraint ensures each vehicle can depart at most once, which is a standard way to represent a single route per vehicle. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. The linking constraint connects deliveries to visits. If a vehicle delivers a positive quantity to a customer, the vehicle must visit that customer in its route. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. This slide shows a subtour elimination constraint in MTZ form. Its purpose is to prevent cycles that do not connect back to the depot. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. This slide summarizes variable domains. Routing is binary, delivered quantities are non-negative, and the auxiliary variables are non-negative. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. This figure shows the core concept. One customer's demand can be split across multiple vehicle visits. Operationally, this helps fill vehicles and reduce wasted travel. In practice, you use these components together to ensure the model is both operationally meaningful and mathematically complete. Tier 2 uses the sweep heuristic. Customers are ordered by polar angle around the depot, then grouped into routes by scanning through that order. The split delivery modification is simple but powerful. When the next customer does not fully fit, the algorithm delivers the remaining capacity as a partial delivery and carries the leftover demand forward. Here is the step-by-step sweep logic. First, convert customer coordinates into polar coordinates relative to the depot. Next, sweep through customers by increasing angle. Then build routes by adding customers until capacity is reached. If a customer's full demand does not fit, deliver what you can, close the route, and continue later to complete the remaining demand. This figure visualizes the sweep ordering and how it supports route construction. The idea is to build geographically compact routes by following angle order. When split deliveries are allowed, the sweep method can use remaining capacity rather than wasting it, which typically improves route efficiency. This slide explains why split deliveries help within sweep clustering. Without splits, a single large customer can force an early route closure, leaving unused capacity. With splits, you can use the remaining capacity to deliver part of that customer's demand, which reduces inefficiency and can reduce the number of routes you need overall. Tier 3 uses ant colony optimization. Artificial ants probabilistically construct routes based on learned pheromone trails and a greedy heuristic such as inverse travel cost. For split deliveries, the ant must track remaining vehicle capacity and remaining customer demand because customers may need to be visited multiple times. This slide describes the transition probability conceptually. Pheromone represents learned experience from good solutions, and heuristic information favors short or cheap moves. By balancing these two signals, ant colony optimization explores many route patterns while reinforcing those that lead to lower total travel cost. Handling split deliveries changes what it means for a customer to be completed. When an ant visits a customer, it delivers as much as possible given remaining capacity. If the customer still has remaining demand, that customer stays eligible for future visits, potentially by another ant or another tour, until the remaining demand becomes zero. This figure shows the split demand behavior in the ant colony setting. A customer can be visited multiple times and by multiple ants in order to satisfy the full demand. That modification is what makes the method compatible with split deliveries while keeping the ant construction process simple and local. Tier 4 uses reinforcement learning with a graph representation. The state captures customer locations and remaining demands, along with vehicle positions and remaining capacity. The key difference from standard routing policies is that each decision includes both where to go next and how much to deliver when you arrive. This slide breaks down state, action, and reward at a high level. The state is a graph with node and vehicle features. The action chooses a next customer and a delivery quantity. A common reward design penalizes total distance traveled and also penalizes using more vehicles. This encourages compact routes and efficient fleet usage. This figure shows a graph neural network policy architecture. The graph neural network builds embeddings that capture spatial context and remaining demand structure. A policy head then produces a distribution over customer and quantity choices, and the model can be trained with policy gradient methods such as proximal policy optimization. Tier 5 introduces a digital twin. It is a real-time virtual replica that combines static network data with live signals such as GPS, traffic, and new orders. The key capability is live re-optimization. When conditions change, the twin can trigger replanning and may resplit future deliveries across vehicles to protect service levels. Tier 6 shifts to a decentralized multi-agent system. Vehicles act as autonomous agents and bid for delivery tasks. By defining tasks as customer and quantity pairs, split deliveries become natural. Continuous bidding and rebidding lets the system adapt as vehicles move and disruptions occur. Tier 7 is the Centaur model. The planner can interactively modify routes and split quantities, while the AI recomputes impacts in real time. Explainable reasoning is essential here. When a split is recommended, the system should explain the distance and time savings and the capacity feasibility logic. Tier 8 adds an ethical framework. Efficiency-only optimization can create unfair patterns, such as consistently assigning the worst routes to the same drivers or delaying service to certain regions. You can mitigate this by adding fairness constraints or fairness penalties that balance workloads and delivery times while still keeping cost under control. Tier 9 introduces a quantum-inspired view using the quantum approximate optimization algorithm. The objective and constraints are encoded into a cost function with penalty terms. A quantum circuit alternates between cost and mixing operations, and a classical optimizer tunes the angles to increase the probability of measuring a low-cost routing solution. This figure shows the conceptual structure of a QAOA circuit. The key point is that the algorithm uses parameterized layers that are tuned classically. After tuning, the final measurement produces a candidate solution that can be decoded into routing decisions and, with appropriate encoding, split delivery assignments. These practice questions are designed to test both modeling and intuition. Start by writing the exact constraints for split deliveries and the visit linking logic. Then reason about how heuristics and learning-based methods handle variable demand, incomplete capacity, and the operational consequences of splitting versus not splitting. Split deliveries provide a practical lever to improve routing efficiency in real last-mile networks. The key is that flexibility in quantities reduces wasted capacity. A complete toolchain ranges from exact mixed integer models to heuristics, meta-heuristics, learning systems, and real-time digital twins, with governance and ethics built in as the system scales.